I'm Stephen Ridley, and today I'm going to give you an introduction to the enhanced security module for SAFERTOS. This layer, this module that we're adding to the thing, was the result of a program that was put in place to satisfy the needs of ISO 21434. The process of analyzing the standards, going through the TARA process, generating security requirements, is kind of out of scope of what I'm going to talk to you today. We do have a white paper that is available on our website and can be downloaded if you're interested in the trials and tribulations it took to get to the set of requirements that ultimately became the enhanced security module. So we at SAFERTOS are all about our functional safety and its applicability into our RTOS product. Applying security to it is kind of the same but different. Vehicles are becoming more interconnected, more complex, so as well as the safety necessary to work in a hazard environment, we also need to protect against outside attacks, malicious intruders, and so on. So they're kind of the same things that we need to do. We need to protect our systems, and we need to make sure that they are as robust and as safe as possible. So when it comes to determining what we need to protect, it's worth having a look to see how a SAFERTOS would fit into a typical application. The simplistic case, where you've got the classic ECU that's performing one function, it's only there, the producer is writing all the application code, they've brought the RTOS in, they've linked the application, they've built it. In this scenario, it's quite defensible to draw the threat boundary around the whole ECU, which kind of means that from an RTOS perspective, you don't need to worry about extra security. It's enough to implement protections or protocols on the communication bus and the usual things you would have to do with root of trust and protecting of the physical access to the ECU. When we come to a more complex system and chip type application, where one person or the ECU manufacturer may not have control of all of the software that is being deployed within the system, then it is perhaps more appropriate to consider a more complex threat boundary. So in this case, we've made the assumption that SAFERTOS is our asset. This is what we're trying to protect. Therefore, any interaction that SAFERTOS has with either the hardware, the application software, or the kernel functions, these are the things that we need to be applying the protection for. And hence the production of the enhanced security module, which essentially is a layer that acts as an interface between the RTOS and the application, and provides a number of security enhancements or features. So this is just introducing that again. We've got our application code sitting on top. It's interfacing to the RTOS core through the enhanced security layer. To achieve this, we do need an enhanced portable layer. So the interface between the bit of the SAFERTOS code that manages the interface to the hardware also needs to be security aware in this case. But the major components of the enhanced security layer are an access control policy. This is where we are limiting access to certain API functions based on the task that is running. An object access control policy, which is where we're limiting access to kernel objects, queues, timers, mutexes, semaphores, etc., based on the task that is running again and whether they are configured to have access to those objects. We've broken the link between hard physical addresses and object handles. This again was identified as a security vulnerability. If somebody has gained access to the system, knowing the addresses where they can cause the most damage is obviously bad news. This atomic kernel transition is really the guts of the security-aware portable layer. There were a number of exploits identified by where the elevation of privilege into the kernel and coming back did allow exploits where the user code would gain elevated privileges within the system. And then also data isolation, which involves making sure that the data that the RTOS uses is protected from direct access by the application code. And finally, penetration detection. We want to know if somebody is trying to poll the system, compromise the system that way. So these are the main features of the RTOS. I'm just going to talk a little bit more about each of these in the next few slides. So, firstly, the access control policy. An RTOS is a toolbox. It has a very rich API, which allows any task to create other tasks, create queues, delete tasks, elevate privileges, reduce privileges, and generally do a whole bunch of things that a safety application probably shouldn't be doing. So as part of the ESM, we've put a mechanism in place whereby a task that is running can only use the API functions that have been configured during the boot phase. So in this very simple example, we have two tasks. Task A is allowed to send to a queue and to check how much data is in the queue. And task B is allowed to receive from the queue and also check things. So basically, if these tasks try to do anything else, an error would be triggered and it wouldn't be allowed. In a similar vein, the object access control policy configures which queues these tasks have access to. So as well as restricting which API functions they're using, we can also restrict which queues or other kernel objects that the task has access to. So in this case, these two tasks are allowed to communicate through Q1, but not through Q2. And as I said earlier, with regards to handle obfuscation, breaking that link between physical addresses and the real the object handles which are provided to the application to reference tasks and queues and things, provides an extra layer of security. So there is a handle registry within the ESM, which is to do with converting the public handles into private handles so that the RTOS deals with that as we go through. Also, the data isolation. SAFERTOS, via its MPU or MMU configuration, has protected its own data for many years. That has been a standard part. But with the ESM, we've moved what was a recommendation into a rule that any TCBs, queue data objects, timer data objects, etc., must be allocated in the kernel data region. This means that the tasks don't have any direct access to these objects. They're just referencing them through the public handles. Penetration detection, this again is essentially a complicated way of saying a centralized error handler. So if an API function triggers an error, then instead of returning straight to the application, this will be routed through an application callback function. This gives the application designer the ability to check that the multiple accesses haven't been done and deal with the matter should there be some polling or interrogation going on. And finally, thank you very much for your attention. If you need any more details on the enhanced security module, please visit us on our website.